So the first thing I want to do is obviously acknowledge all the other people who have worked on this software project. And it's now about 60 PhD students in Berlin, my group, and elsewhere who are working on it and taking forward. I'll show you more about the project as such. Now let's see how I can make sure that you see the next slide. Okay. Anyway, before I start, I want to talk about some of the basic assumptions which go into transport models, because they help you to understand why certain results are necessarily given when you take these approaches. The first thing is that transport models, in one way or another, talk about what is the individualized generalized cost of travel. So the idea is that travelers experience certain costs and make decisions based on them. And these costs are the decision-relevant generalized costs. So these which are they immediately see and experience. And there are all the overlooked individualized costs. For example, car drivers don't think about the fixed cost of their car. And from a social point of view, because transport planning is looking also at the governmental decisions and therefore the social point of view, we also have to look at the externalities. So all of these things have to be calculated in a transport model. Now, but what are these generalized costs? I'll come back to that in a second. The second key assumption is that transport systems are systems of queues. And we have to understand how these queues form and dissipate. And therefore, we have to look both at the behavioral assumptions about the generalized cost, as well as the technical assumptions of the formation and dissipation of queues. And these queues arise when the number of slots to help serve them are exceeded by the current demand. You know that very well. Whenever you are in a meeting room and everybody tries to leave, the doors are too small to get everybody out. You know that the moment you stand on a motorway and there's traffic in front of you. You know that when you're standing in front of a signal, there is a queue which is managed because there is not enough space in time and space to move you. Now, these slots obviously don't fall from heaven, but are decided by societies. And this is where transport planning comes in. It helps societies or private firms to decide on the number of slots which they want to offer. And societies do that by designing and operating the road and rail network. And this is not made as explicit, they decided to reach certain desired speeds. So there's certain quality expectations for the firms or societies behind, which are then expressed by the numbers of slots, i.e. the rail network, the rail services, the road network, the services on the roads, which enables those speeds to happen. Now, one of the issues then is that travel demand, i.e. the desire to travel, is a normal good, i.e. it grows when individualized generalized costs decrease. So we are a bit trapped because anytime we expand the road system, we invite more travel. And in most cases, this is a desired outcome because that allows people to participate in social life, working, seeing the people they want to see. This allows firms to deliver goods and services to wherever people are. Now, there are downsides to it, all the externalities I mentioned before, but that's the essential bind we are in. Now, as a second bind we are in individually is, in general, we choose the average level of the generalized costs for us. Why do we do that? Because we decide where to live, where to work, and what mobility tools we own. What are mobility tools? Mobility tools are all devices where you trade off a one lump sum payment against improved service later. The car is the classical one, or a season ticket for public transport, and even your bike. You trade off a couple $100 or a couple $1,000, depending on taste, on something which allows you to travel much faster than walking. So these decisions are taken given this, the environment in terms of the speeds offered by the societies and the living possibilities given by societies. So everybody would like to live in New York, but not everybody can. So we have that as a further choice dimension, which we have to look at when we look at transport demand modeling. Now, when we have this model, which allows us to describe the environment, to describe the networks and its physics, to describe the demand and the externalities arising from it, what are the tasks we are given by society or firms? They differ because the time horizons for which we have to make forecasts differ. And matching to those time horizons, the models differ because sometimes it's overkill and sometimes it's just not good enough. So for example, if you have a public transport undertaking wants to introduce a new transit line, a new bus route, they want to know what happens in half a year. So they have existing data. This is marginal change, so they want to know, for example, a new line, a new timetable, some new parking fees. That's short term from transit planning point of view. Then you have something bigger, let's say a new transit network, kind of the routes are completely changed and reformulated. There's a new business park, there's a new mall. What's going to be the impact of that? So this will probably take a year or two to go through all of the behavioral changes. So we have to make forecasts for a 2-year time horizon. But then when it's a massive investment, for example, think of a new motorway, think of a completely new high-speed rail line, this will have to be evaluated over a long time horizon. For example, the Gotthard Tunnel, which was built in Switzerland, if you want to assess its benefits, you have to do it essentially for 100 years, because otherwise it will never pay off. Now, as you can see from those differences, that the models have to be different and the data requirements which go into them. Because, as I said, for the half-year time horizon, you essentially just extrapolate from current conditions. But for a 40-year forecast, you have to look at all the other changes as well, which come in. Sorry. Now, so how do we model this? In essence, all the transport models try to forecast the generalized costs of travel, these Ks, for a particular time, for a particular place, for a particular group of people in a particular year in the future, or it might be this year. As explained from the basic assumptions, these generalized costs, in particular the congestion or crowding, is a function of the demand. How many people are there? How many trucks are there? And the supply of the services. Now, unfortunately, the demand is again a function of the costs, because as I said, it's a normal good. The cheaper it is, the more we consume of it, and the number of people in the area, B. So we have K on both sides of the equation, so we can't solve it with closed forms in the general case. So what we do? We sometimes divide up these general formula into two sub-models. We have a model for the supply side, where we look at the change of generalized cost as a change in the supply and the demand. And we have a demand model where we look at the change in demand as a function of the costs. And by tradition, the communities which build these models, these two models, are separate. So you will have specialists which only look at the supply side models. You will have specialists which only look at the demand models. And you will find that MATSim is unusual because it brings both things together in the coherent framework. And there is no standard model for either task. So you'll find endless numbers of detailed model specification to solve this task at hand. Now, what is a generic model structure? You will find in all approaches in the field. Let's start on the left. There will be models there will be a model, which is essentially the supply model, which looks at the competition for the slots in the facilities and in the network, given the demand. Models which tell you about how fast people can travel, how crowded it is, how comfortable it is. This model, submodel, tells you about the generalized cost K coming out at the top. And these generalized costs now are combined with the population today or in the future, described in as much detail as you wish it to be and as you need it to be. It is combined with what the betas, which are the taste parameters. So how do people prefer to decide on routes, on modes, on destinations, how many people want to buy cars or not? They are combined with that estimate of generalized cost, and then we decide on the scheduling. So what trips, what movements will people make in space? And that is now the demand. And the demand is again fed back into the competition model. And we do this till we have iteratively reached an equilibrium, i.e. a state where there is no further change likely, as we assume that everybody, all the agents have found their optimal route given their preferences, their locations, their mobility tools in space. And the scenario essentially then allows us to change this. So a new railway line, a new price schedule, whatever we have, we want to analyze, we will then put in and see what the new equilibrium outcome is. As you can guess, this is a computationally intense, and the more detailed it is in space, in time, in terms of the population resolution, the more computing time you need. Now, why do we calculate this equilibrium? Because it's obvious to everyone that travelers aren't in equilibrium, because you have new ideas tomorrow. Your wife has new ideas. Your partner has new ideas. The government has new ideas. And then in the equilibrium approach, because it's an optimization approach, we assume that travelers know all the alternatives. We have assumed, so to speak, that everybody has Google Maps in their mind and knows exactly what the travel times and costs will be. And then we do know that people don't plan a whole day in advance, because that's what the model always also assumes, that we look at the whole day. Now, why do we do this? Because the equilibrium gives us something which we can compare with each other. So in particular, if we have multiple options, we can tell the client that this will be the likely impact of it. Now, I have to do a bit detour in what the labels of our models are, because transport planning is around for the last 70 years, so it has developed into different directions. But before I go there, I want to present something which is important, because, as I said, these transport planning models are computationally intensive. They take quite a long time to establish, estimate, validate, and calibrate. So for certain questions, it would be nice to have, in essence, a shortcut. For that, I have to acknowledge some colleagues who worked with me on this. Now, the idea of this shortcut is the fundamental diagram, which describes the road network as a trip processing factory. And I'll show you an example in a second. And each of these MFDs has an optimal point where it describes for us the capacity of a downtown area. And it's bigger than a downtown area. We have estimated these things for areas of, let's say, 20 square kilometer size, so sizable parts of a city. And what is important, the MFD is only a function of the network and is not related to the demand. So it's physically independent of what's happening in the demand side. And here are examples. These are empirical MFDs, which we estimated for Zurich, for London, for Strasbourg. And you can see that depending on the city, the points of capacity changes. For example, if you look at let's say the point in the red cloud, that's London, you see that London has substantially lower capacity than, for example, Zurich, but has higher capacity than Strasbourg. And if you look then, this was the relationship between flow and speed. You can also look at the relationship between flow and density, and you can look at the relationship between density and speed. And you can see each city has a different MFD, but they are replicable, they are stable and standard. So you can make use of them for further engineering, in particular traffic control.
So let me make sure I understand.
Yeah, sorry.
What are all the individual points? And
these are, sorry, good, I forgot to tell that. What we do, we measure the speed and density of in the network. Essentially, we observe the flow from loop detectors. These are loop detector-based data, and these are 5-minute values across the town and the city across the day.
So it's like loop means how many cars passed?
A loop is a physical measurement device in the pavement which observes how many cars pass at what speed and how long they stay in the city in that point. And we have multiple loops all around the city, which gives us the basics for this information. The equivalent essentially is taking taxi data. You can estimate these also from taxi data, i.e. we could observe them from Google timeline data as well.
Okay, and each one of those points is a real observation? Each one of those points is a real observation?
These are all real data.
And then what does a critical point mean? Is that a theoretical concept, or is it like that?
Is the point of maximum flow. It's the capacity point of the network. So
and does that depend on the model of flow, or is it independent? Does it depend on the way you model flow, or is it somehow more abstract?
No, it's a measurement. It's an empirical observation.
Okay.
No models. There are certain things involved, but this is an empirical point. So and this is Zurich, you can move in the downtown area 560 points per vehicles per hour in lane.
And essentially, this is the maximum flow.
Yes,
is what it looks like.
Because it's the highest observed. And to this belongs a certain density. So the critical density at which you observe the maximum is at just about 30 vehicles per lane kilometer, and it's at a critical speed of just about 20 kilometers an hour. And you can see, for example, that in Strasbourg, the speed is substantially lower in that central area. Now, the traffic engineers work with these to come up with controls. My PhD students were interested in finding out whether we can explain these critical points. So we did this for 40 cities around the world and about 100 sub-areas in each of those across all of these cities. And we can, for example, show that the critical accumulation, i.e. the capacity of the city, varies significantly with the betweenness centrality of the networks. So we had the networks, we measured the betweenness centrality of each of the links in the network averaged it across the links of that network, and and lo and behold, the more likely you are to get avalanches, kind of looking at complexity theory, the more likely you are to have lower capacities. Now, we have done this for 110 sub-areas of 40 cities, but we would love to do it for hundreds of cities and thousands of those areas.
So I'm a little surprised that the relationship is more or less single mode. I would have expected like Indian, Chinese cities where the traffic rules are obeyed less to have a different distribution.
I think the point was we didn't have Chinese cities because the Chinese, we did approach them, but we didn't get any data out of them. There is actually a Tokyo point in there. There's American points in there. There are European cities, and the paper is actually online. So let's move on.
Okay, so these, yeah, traffic behavior does not change anything across those kind of category of cities, but
no, it's surprisingly little impact.
Interesting. Okay,
but we would have to verify it because we didn't have, let's say, African cities.
Perfect example. Yeah, the driving style is different there.
Yeah. Now you can actually extend this analysis into multiple modes, and we have done so.
Right.
We looked at the interaction between buses and cars, and in the MFD, you can theoretically describe what the maximum permissible flow is, and you can then look at the observed points. And in London and in Zurich, we had observations for both buses and cars. And as you can see, the red points stay below the envelope, which is the theoretical maximum envelope. And we have since expanded it to include bicycles as well. Now, what you can also do, you can interpret the distance between the envelope and the points as a measure of the quality of traffic control. So this actually hopefully will help cities to compare themselves against others and to try to learn from them. Now, this is a detour because with all the data which Google has, you could estimate these as well. And I do know that there was a project in the Netherlands where Dutch data were made available to estimate these things. And it would be really interesting for us to do this, not only for one country, but across multiple countries to get at your point of different travel behavior or traffic behavior. Now it gets back to the models. Now, what are the difference you can have in transport models? There's the question of resolution. So do you model agents, i.e. software entities which interact, or do you model flows? Do you assume that there is zones generating flows? Then the spatial resolution. Do you have zones, i.e. large chunks of a city? Do you model each individual parcel, or do you even individual units inside the parcels? Then you have to ask yourself, how do you describe the travel behavior? Do you describe it as individual trips, i.e. movements between activities, tours, or the daily chain? How do you model the choices made? Is it discrete choice models, econometric models? Is it rule-based models? Or today, machine learning models to predict what choices people make? Route choice. Is route choice fully integrated in the model system, or is it kept separate? There is a tradition of models where demand is generated and then a separate model is used for route choice. How do you construct the choice set? What do people know? Between what do they decide? Is it explicit or is it implicit? And then how do you solve it? Is it an MSA, an average? Is it a sample enumeration process? Is it co-evolutionary search? And finally, is the equilibrium reached across the whole schedule, i.e. all the activities of the day, all the trips of the day together, or is it for each trip separately? Now, there are a couple more slides in the appendix which shows other approaches, but I will only talk about MATSim because that's what this is about. MATSim is an agent-based model. It allows you to choose the spatial resolution, but in the most detailed models we have built, we essentially model individual buildings. The scheduling model looks at the whole daily chain and all the interactions within the day. The choice model, we use rules and heuristics, but we also use discrete choice models. Rule choice is fully integrated. The choice set construction is implicit. We use co-evolutionary search, and it's a scheduled equilibrium. Now, how do we go about this? Before I get there, I will want to say a bit about what MATSim is. MATSim is a GNU licensed open source project, which has been developed for the last 15 years, first at ETH, then in Berlin, and now both in Berlin and Zurich. The main partners are Professor Nagel in Berlin and at ETH, and that includes a group at the Future Cities Laboratory in Singapore, which is a dépendance of ETH there. But since then, in particular in the last couple of years, lots of other people have started to join. Most importantly are the two immediate spin-offs of Kai and myself, Zenozon and Zimuntu. Then the Swiss Federal Railroads are now using the model for their own internal planning purposes. They built another Switzerland model, and there are other universities around the world and firms which are using it. And we are happy about that because it provides more power to the further development of the tool. We know for about 45 implementations around the world, matching number of research groups, mostly research, but now commercial uses. And the software itself is based on Java. We run daily tests on the system. There's a stable APIs for the different modules inside the software. And there was a last major re-implementation about 6-7 years ago. And we'll see what happens next. That gives you an idea of the cities for which we know that models exist. There are probably more. The largest models are a model of all of Germany with 80 million agents. There's a couple for between 5 and 10 million agents, and then there are plenty smaller ones all around. We have now lost track of everybody, so this is probably an underestimate of where we are. Now, I'm not sure whether this will work. Let's try. What I show you here is Singapore, and this visualization was done by the colleagues in Singapore. The white dots essentially show you where activities start, and now you can see that we are actually moving the vehicles in the network. And we do that for both cars and public transport vehicles one-to-one. This is just a bit of eye candy showing you that we do what we promised to do. So let's, what's happening now? Good. Now, what is the base approach in the model? The base approach is similar to the approach I showed you 15 minutes ago. So we start by generating the initial schedules, i.e. the plans of the agents, where they want to go, by what mode they want to go, when they want to go, how long they want to stay at the destination. We then model the traffic flow, as you saw in the last little video. And the model we apply there is a very simplified description of the traffic dynamics, but consistent with what we know about the traffic dynamics and able to generate realistic estimates of speeds and realistic estimates of crowding inside the buses and trains. We generate the costs we average them in 15-minute bins and calculate the utility of the day. So how good this day was for the agent. And that depends on when he starts and when she wants to leave. Then, based on this, we replan. We give the agents the chance to optimize their decisions across all the different dimensions of daily behavior. And I'll talk about that in a minute. These new plans for their selected agents are put back into the simulation. And we repeat till the score reaches a stable state, like you can see here. So the average of the executed plans, the orange line, gives you an idea of how that works. So in principle, you start essentially in a status of ignorance, and the system then converges. But you need a couple of hundred iterations till you're sure that the system has converged. And this is where the computational costs come in. And we are continuously working to make that faster in various ways.
So let me ask you this.
Yep.
You motivated the use of equilibrium
Yep.
as kind of the benchmark against which you should judge other things.
Yeah.
Are intermediate solutions valid approximations of non-equilibrium dynamics?
This is a question which has been asked for all transport models, not this forever. They probably aren't.
Okay.
Because you can think of this not as learning in a sense in which you and me are learning a city and therefore adapt the behavior. And it's a mathematical approach to get to the final point. It would be interesting to be able to observe learning in real time. Now, Google does that all the time because you have all the data you put into Google Timeline. But that amount of data is infeasible to collect for any research project. And there were attempts to do that with samples of 50 or 100 in either real life or in simulation environments. But to do it at scale, we would need to do something of the power of either, if you're only interested in cars, you could do that with TomTom or here. But if you want to do it with smartphone data, you would either have Google or you would have to have your own app. And we are using that own app. We have currently a study ongoing where we have 3,300 people tracked for 8 weeks, but only 8 weeks. So this would an obvious way to make good use of the data Google Alphabet collects to understand what is actually happening here.
Yeah, makes perfect sense.
Now, what are the issues we have? Obviously, the size of the search space is enormous because of all the behavioral dimensions you have. Starting time, duration, the modes, the routes, the destinations, it explodes. Then you have to look at the rate of replanning. How quickly do you allow people and how many people, agents, do you replan? What is the choice set? That becomes then an obvious issue for the computing because you have to keep it in memory. And even the biggest computers, at least the ones we have available, kind of hit their buffers there. Then there are more technical questions because the solution space kind of converges too quickly. So we would be interested, just as you are whenever you do genetic algorithms, to be sure that there's enough variance from which the agents can learn. You want to actually generate what is called a log sum term for welfare calculations. And finally, we have looked at the stability of the equilibrium at the average. But for example, the SBB and the clients will be interested at very, very detailed levels to look at that. And there is still too much variance in the procedure. So the client or SBB wants to have more certainty about the results. Ongoing work. Then, just to remind you, what are the dimensions of choice? What we would be interested in is the number of and type of activities. So how many things do you do and what you do, in what order. That is in itself an NP-hard problem. Then you have to look at the start and duration of activities. Then, if we really were complete, we wanted to understand who's coming along. So how big are the groups and how do they divide up the costs? Because it's obviously something different if your boss takes you to dinner than if you have to pay yourself. Then where do you do that? Then how do you move between the locations? And that, again, has sub-problems. So you want to know where you get to your vehicle. Where does it stand? Where do you pick the bus? Where do you park? Which vehicle did you choose to use, in particular, when you think about public transport? What route, what service do you use in the system? And then again, who's traveling together and how you split the cost. So these would be the dimensions we would like to look at. And there's work ongoing on all of them. PhD thesis, other research projects, which try to address each and every one of those problems, to integrate them into the system to arrive at a fuller description of what is happening. The red ones on the screen are the ones which are currently implemented in the standard MATSim you can download from the open source archive. But we are trying to get everything integrated. And this is, in a way, the research program which we have. The utility function is actually inspired by Vickrey in his work on departure time choice in the 70s, 60s, 70s. It's a linear additive model where we say we add the utilities of the activities and the disutilities of travel. And for the activity utilities, it's a function of duration, and there's a penalty for arriving late. But the question, what hides behind the use, and we could or would like to expand those formulations to make them richer behaviorally. Now, I want to show you an example how we can put this to work. And I'll do that with the example of automated vehicles. As it's no surprise, all of transport planning is currently looking at the impacts of automated vehicles, and in particular at the impacts of automated taxis, which seems to be the most likely first incarnation of these vehicles. We did a project or a series of projects on this, and in the first project, Sebastian Hörl looked at the simulation of the taxis and their dispatch and repositioning. Felix Becker did the stated choice experiments to look at how people would choose and buy them. And the three of them at the bottom looked at likely costs. We came up with estimates how much these services would need to cost if they had to pay their full fare. What we did, we took MATSim on the right and added a module which essentially dispatches the vehicles to the demand as mobilized in MATSim. So this is the core system, which the simulation, scoring, planning, and there's an external module which essentially allocates a taxi to everybody in the system who has said, I want a taxi. And there's different optimizers and different tools, and they have impacts in terms of waiting times and empty mileage. What the system does is it simulates for a given fleet. It then calculates how well the performance was, in particular, how many empty miles it produces, how occupied the vehicles are, and how many people actually are paying for the service. Based on that, in particular on the empty mileage and the income, we recalculate the costs, the prices which the operator has to charge, and then update the price which is charged. So then we have a new price, and the simulation returns and sees how many customers it will win. This in itself, obviously, is again a new further iteration on top of everything else. But in our examples, and we did a couple now, the price will converge to a fixed point, and the demand will arise. And with that, we then also looked at finding an optimal fleet size in terms of how large a fleet can actually survive. When you have that, you can then ask, okay, what's going to happen? And what we did, sorry, this is in German because the English paper is still being written up on this work. We modeled the base case, and we looked at the results here in terms of passenger kilometers traveled. And this is just for the city of Zurich. We actually looked at the whole region, but just to make it simple. And the city of Zurich, you have about 1.2 million person vehicle kilometers of travel. The bulk is individual cars, and then there is about not quite 150,000 kilometers in buses and trams. We kept those constant. We didn't change that. We tested whether lowering the price of public transport would reduce individual usage. Yes, it did. It did. And the elasticities are in the order of magnitude you would expect. Now, after we did that, we allowed an AV taxi fleet to compete. And two things happen. A, buses and trams, the timetables are unchanged, but the AV taxis are able to attract people out of them. They attract both people out of their private cars, but in principle, they attract people out of their buses and trains. And the total amount of total mileage increases because the AV taxis service their customers. They drive empty from customer to customer. So in total, it has an impact. And this is at the competitive price where they can still survive. Then we tested it again with half price public transport, and you see the shift. And it comes both from individual vehicles as well as from AV taxis, less so. And then in our model, we allowed private ownerships of AVs. This is obviously hypothetical because you know that as well as I do that it's unclear when these will be made available. But in our model, we assume that people look at the price. And we made the assumption that people forget the fixed cost of their cars, as they do today. And if you allow for that, the AV taxis are wiped out in our model because we have too few people coming from the outside which don't have available a private vehicle. So essentially, the private AVs will wipe out the taxis because the perceived cost are a third of the cost of a taxi. Now, this is Zurich. Maybe in Manhattan, maybe in the center of London, this will be different. But this raises to us a big question whether AV taxi fleets will survive if you allow private, individually owned AVs. Now, what are the challenges? First, there's lots of things.
One quick question in
Please.
that, in the private AV model,
yeah.
Does the owner need to find a place to park for the day, or are the additional miles, for instance, the vehicle moving to some distant parking?
In this case, we assumed, and this is to do with the fact that modeling parking is a whole other challenge of its own, that the people still have the parking spaces they currently have. So there's no assumption that the fleet increases, so people can park where they park today. So you're right, we didn't explicitly model constraints on parking, and this will be the next thing to do. But modeling parking is difficult because in general, let's say in Europe, people have to search for parking. So there's there's a whole choice model in its own right, and there's a whole process, and it kills you computationally. So we kind of simplified this away.
Right, exactly. And that's one of the things I was getting at, is that in some of the larger cities, if you just look at the prices charged for parking garages in Manhattan or San Francisco or Boston or any of these places, clearly satisfying that need to park is worth some significant amount of money.
Yes.
That even though a driver will, as you say, forget the fixed cost of their vehicle, they don't forget the price of parking.
They will, because most of these people park in garages paid for by their employer, or they are on business visits where they charge the client for the parking. So yes, parking is a big reason why people don't drive into cities, but you have to ask the question, how many actually pay themselves? And yes, parking is a big issue. I agree with that, and we would love to extend that model in this direction. But just practically, there's issues like many cities just don't know how many parking spaces they have and where they are. It's a massive data issue they're involved in as well. But agreed, more work needed.
Well, let me ask you a different one. If I am trying to figure out like a delivery company thing where I want to see how to route deliveries in a given traffic environment, it seems like a related problem to what you just modeled, right?
Now, agreed. Now, in this model, we didn't include all the package delivery services.
Yeah.
Because again, a data issue. The DHL, UPSs of the world don't share their data. So we don't know how these deliveries are distributed in space. We are currently doing a small study where we will try to get at this by looking at how many packages do people actually receive. There's a whole.
Okay, that would be cool.
So what are the challenges? There's obviously, you can make this, you can change some of the techniques which go in, for example, the econometric estimation and machine learning techniques to update the choice models embedded in MATSim. I didn't talk about population synthesis, the choice of workplace and residence, the choice of owning cars and season tickets, and then how do you capture travel behavior as such? For example, do you use, as your granddad did, paper and pencil surveys, or do you rely on the equivalent of smartphone apps to track people? Then how would the land market respond if you change the transport system? How would the labor market respond if massive investments happen? There's work, but you can do more. And then obviously all the questions about how you design the networks, timetables, the networks optimization. How do you choose technology for technologies? For example, where do you put all the charging infrastructure for electric mobility? All of these things have to be added and are being added in particular applications and need to be added further. And then just for MATSim itself, we would like to have a coherent estimate of that utility function I showed. At this point, we have put it together from experience and the literature, but we have never been able to estimate it whole. And the reason for that is essentially lack of data, because there are so many free parameters and so many different conditions that the standard surveys which are available today are unable to do that. Then there's the issue of the implicit choice set. Then there's the logsum term for welfare assessment. Then we clearly want to make it faster on all fronts in the system. Then, because our agents are smart, we never get them to gridlock, because gridlock essentially is a signal of being uninformed. Then, next thing is we are working on generating artificial social networks. So our agents know each other, our agents could talk with each other, and influence each other, particularly on the leisure front, because leisure makes 40% of miles and all trips. And finally, we have to ask ourselves, are there equilibria when we introduce multiple agents? For example, what happens when you have a taxi operator and have multiple taxi operators? How do they compete with each other? What happens when you have multiple store chains and they compete with each other? When you have multiple information providers and they provide different information to different clients, what will happen with that interaction? All of these we would be interested in to explore, given the computational resources and time to do that. And with that, time for further questions. These are kind of a couple of base sources. MATSim.org is the website where you find a book which describes the system as of 2016. There's the code, there are examples. You can essentially download and get it going. The next two are references to my group and the group in Singapore, and finally the two spin-off firms which are offering the service. Zenozon is building models and selling the data they generate with it. Zimunto looks more at tools to evaluate the results which come out. Good. Now, questions. Variance or reliability is a big issue. That's true. But the impact of reliability is substantial, but not that large. Now, how would we do this? For us, the computation of the equilibrium for one day takes us, for let's say Switzerland, a couple of days to do. Now, if you really want to look at variance, you have to do multiple days, or actually weeks. So this is difficult to include in transport models. There are various ways of doing that, and you can include it, for example, in the choice models for the routes and the modes, and that has been done, and we could do it here. But if you really wanted to simulate it, it would be computationally very expensive. Coming back to the question, what drives a choice? One thing one has to remember that public transport, on average, is about 3 times slower than driving in a car, and this really makes up the decision to a large extent. And in those areas where public transport is competitive, tend to be few. It's the places where there's congestion. It's the places where there's no parking. And it's the places where you are charged to get into town. Everywhere else, public transport has a problem.
Those are public policy questions then.
Yeah.
Okay. I think that's all the questions online. But yeah, well, thank you very much. It was fascinating. I think I have a few more folks who spoke about this that I think would be interested in the recording.
Yeah, I'm fine. I'm open for any further person who has questions. My email address is known, so please get in